Okay, so we've taken our derived equation. Now what do we do with this? So let's take a look at this sort of separated, this equation sort of separated. So this is the same equation that we derived in the last video, but I've rearranged it just a little just to separate two specific terms here. So one is this K2 times E naught term, which is in the numerator, and the second is this term here, where there's S naught over S naught plus Km. Now note, Km is something that has been substituted, and that was this complex this complex term with rate constants, which was equal in the last video to K minus 1 plus K2 over K1. So this on the bottom is known as the Michaelis constant. Okay, and that's denoted by large K and over large K with a subscript uppercase M. Okay, and if we look at this term, what we see is we have S naught in the numerator and then S naught plus Km in the denominator. And so this looks vaguely familiar to our ligand binding equation for myoglobin, where we had, instead of S, we had L naught all over L naught plus KD. And so this takes the exact same form. And remember, this is a hyperbolic equation, which means that it saturates. And of course, that makes sense in a physical sense for myoglobin, because we can only so much ligand can bind to so much enzyme. We can't go over 100% of sites of enzyme. So this is a similar effect here. So what this indicates is that we have a hyperbolic part of the Michaelis Menten equation that dictates how many of the enzyme substrate complex we have, which then dictates the overall rate. So that's one part of the Michaelis Menten constant. So we can think then of the same way that what we would expect then is that if we have different initial substrate concentrations versus rates, what we would expect then to see several points that begin to saturate at some asymptote. We'll color this red so it's easier to see. There we go. So that approaches an asymptote, just like the ligand binding curve does. Okay? And then the same way that we found KD from a plot like this for ligand binding, we can do the same thing. So if this is our maximum velocity, at half of that maximum velocity, so we'll term this Vmax, at 0.5 maximum velocity, if we have a Michaelis Menten plot, we can project down to the substrate concentration, and that is going to be equal to the Michaelis constant. Okay? So the Michaelis constant, all it is that when the substrate concentration is such that it is 1/2 Vmax. All right? It's very analogous, again, to our ligand binding equation here. All right? The second part of the term dictates how fast the reaction can go, even at saturation. So this is K2 times E naught. So that is equal to, we call this Vmax, this term here, okay? And that's the same Vmax here. So that's saying that when this is saturated, so when substrate is at its highest, is saturating the enzyme sites, then Kn is going to be very small. This is going to be equal to S naught over S naught. That's going to be equal to 1. And the velocity is going to be equal to V max, which is going to be equal to K2 here, times the enzyme concentration. And so that's our highest concentration that we can get, or sorry, our highest velocity that we can get. And then from there, if we have V max and we know the enzyme concentration, then we can calculate K2 for this reaction, which is part of, which tells us how fast this second part of the reaction is versus here.